Section: Introduction. In this section, we introduce self-evolving large language models, LLMs, which hold great potential for enhancing language intelligence. These models can independently generate, refine, and learn from their experiences, paving the way toward advanced artificial intelligence. A key requirement for training these self-evolving LLMs is having access to a large number of well-curated tasks and labels, which guide their learning process. However, depending on human annotators for this data is expensive, labor-intensive, and limits scalability, creating a significant obstacle to developing AI systems that could exceed human capabilities. To lessen our reliance on human-generated data, we explore self-generated and label-free methods that eliminate the need for explicit supervision. One approach, label-free reinforcement learning, derives reward signals from the model's own outputs, such as confidence scores and output variability. Yet, these methods still depend on a pre-existing set of tasks, which restricts their scalability in truly self-evolving environments. Alternatively, self-challenging methods involve training LLMs on tasks they create themselves. While these methods show promise, they often require external code executors to verify the feasibility and correctness of the generated tasks. This verification challenge is particularly pronounced in areas like open-ended reasoning. In this paper, we propose R0, a framework designed for training reasoning LLMs that can evolve without any external data. In R0, we start with a single base model that takes on two roles, a challenger and a solver. These roles are optimized independently but evolve together during the reinforcement learning process. The challenger generates tasks that push the solver's limits, while the solver is rewarded for tackling these increasingly difficult challenges. During the challenger's training phase, it uses group relative policy optimization, GRPO, to create tough questions, with rewards based on the uncertainty of the solver's responses. In the solver's training phase, it is fine-tuned on a selection of these challenging questions, using self-generated pseudo-labels. This cycle repeats, allowing for continuous self-evolution without human input. Our experiments show that R0 is a flexible framework that consistently enhances the reasoning capabilities of various LLMs. For instance, the Qwen 3-4B base model saw an average score increase of over 6 points on math benchmarks after 3 self-evolution iterations. Additionally, the reasoning skills gained from our math-focused questions also improved performance on broader tasks, as evidenced by significant gains on general reasoning benchmarks like MMLU Pro and Super GPQA. We also found that R0 can serve as a mid-training method, where models initially improved by our approach perform even better after being fine-tuned on labeled data. Furthermore, we provide a detailed analysis that validates the components of our framework, illustrates its compatibility with supervised fine-tuning, and examines the dynamics of co-evolution to highlight both strengths and weaknesses, offering valuable insights for future research. In the preliminaries, we build on recent advancements in reinforcement learning for fine-tuning LLMs, focusing on two key methodologies relevant to our framework. The first is Group Relative Policy Optimization, GRPO, which fine-tunes a policy LLM without needing a separate value function. The main idea is to normalize rewards based on the performance of other responses generated from the same prompt. For a given prompt, the policy generates a group of responses, each receiving a scalar reward. These rewards are then normalized to compute a response level advantage. The policy is updated using a clipped surrogate objective, similar to proximal policy optimization, PPO, to ensure stable training. This objective is regularized by a KL divergence penalty to prevent policy drift. By maximizing the negative of this loss, we encourage the policy to favor responses with positive relative advantages while controlling divergence from the previous policy. Section Summary. In this section, we introduce R0, a self-evolving framework for training reasoning large language models, LLMs, that operates without external data by utilizing a challenger and solver mechanism, where the challenger generates increasingly difficult tasks and the solver learns to solve them. Our experiments show that R0 effectively enhances the reasoning abilities of various LLMs, demonstrating significant improvements in performance on both math and general domain reasoning benchmarks. Section: Reinforcement Learning with Verifiable Rewards. In this section, we discuss reinforcement learning with verifiable rewards, RLVR, a method for refining models in areas where we can clearly verify the quality of responses. This method uses a rule-based verifier that gives a binary reward to each generated output based on whether it meets specific correctness criteria. This reward system is particularly useful for tasks like math and code generation, where correctness can be easily checked, and it forms the basis of our reward mechanism in training our solver. We introduce R0, an automated framework that includes a challenger and a solver, both starting from the same base language model. The framework works in a loop. First, the challenger is trained to create difficult questions for the solver. We then build a training dataset of question-answer pairs from these questions using a filtering strategy and majority voting. After that, we fine-tune the solver on this new dataset. This iterative process allows both the challenger and solver to improve together, and the entire system operates without human input. The challenger is an autoregressive language model designed to generate tough questions. We train it using the Group Relative Policy Optimization (GRPO) method, focusing on creating a reward function that reflects what makes a question good. We concentrate on math questions since their objective nature allows us to easily generate pseudo-labels through majority voting, eliminating the need for external verification. To help the challenger create challenging yet solvable questions, we define an uncertainty score. For each question, we ask the solver for multiple responses and take the most common one as the pseudo-label. We then calculate the solver's accuracy for that question. The uncertainty reward encourages questions where the solver is unsure, aiming for an accuracy around 50%. To promote diversity in our training set, we implement a repetition penalty. We use the blue score to measure similarity between questions, grouping them into clusters based on their similarity. The penalty for a question in a cluster is based on the size of that cluster relative to the batch size. A crucial step in our reward process is a format check to ensure each question is correctly formatted. If a question fails this check, it receives a reward of 0, and we do not compute any further rewards. For questions that pass the format check, we calculate a composite reward that combines the uncertainty and repetition signals. We then use these rewards to compute the advantage for each question and update the challenger's policy by minimizing the GRPO loss. Section Summary. In this section, we introduce reinforcement learning with verifiable rewards, RLVR, a method for enhancing models in verifiable domains by using a rule-based verifier to assign binary rewards based on correctness. We present R0, an automated framework where a challenger generates challenging questions for a solver, both evolving through an iterative process that utilizes a composite reward system to optimize question generation and ensure diversity. Section: Solver Dataset Construction. In this section, we describe how we construct the dataset for training the solver. After updating the challenger, we generate a new, curated dataset to train the solver, acting as a curriculum generator. We start by sampling a large number of candidate questions from the challenger's policy. For each question, we gather multiple answers from the current solver, determine a pseudo-label through majority voting, and calculate the empirical correctness. We only add a question-answer pair to our training set if its correctness falls within a specific range, filtering out tasks that are too easy or too hard. This filtering not only helps us focus on appropriately challenging tasks but also serves as a quality control measure. Low correctness often indicates that a question is unclear or that the pseudo-label is unreliable, so we remove these items to enhance the quality and reliability of our training data. Next, we fine-tune the solver on this curated dataset of challenging problems. We use a simpler, verifiable reward signal during this stage. For each question with its pseudo-label, the solver generates a batch of answers, each receiving a binary reward based on whether it matches the pseudo-label. This reward helps us compute the advantage and update the solver's policy by minimizing the loss function. This process improves the solver's ability to tackle the difficult questions generated by the challenger. We also provide a theoretical basis for our uncertainty reward function, which is maximized when the solver's success probability is at 50%. Our analysis is based on recent findings that suggest optimal training occurs when learners face tasks at the edge of their capabilities. We quantify the learning potential of the solver by measuring the divergence from an optimal policy, which is influenced by the variance of the reward. This leads us to a specific lower bound that indicates maximum reward variance occurs when the success probability is 50%. Thus, by designing the challenger's reward to encourage questions that challenge the solver, we create an efficient learning curriculum. We utilize the Quen 3-4B base and Quen 3-8B base models to evaluate the impact of scale within a single architecture. Additionally, we include the OCTOTHINKER3B and OCTOTHINKER8B models to ensure our approach is effective across different model lineages. This is important since previous attempts to apply reinforcement learning to llama models yielded less than optimal results. By testing our framework across various foundational architectures, we can assess its effectiveness. Finally, we evaluate our framework using a comprehensive set of benchmarks. While our question generator prompt focuses on mathematical problem solving, we aim to determine if the improvements in reasoning ability can extend to other areas. Therefore, our evaluation is organized into two main categories. Section Summary. In this section, we describe our process for constructing a curated dataset to train the solver, which involves sampling candidate questions, obtaining answers, and filtering based on correctness to ensure quality and challenge. We also outline our training approach using a verifiable reward signal to enhance the solver's performance on difficult questions, supported by theoretical analysis that emphasizes maximizing learning efficiency through uncertainty. Section: Mathematical Reasoning. In this section, we utilize 7 challenging benchmarks: AMC, Minerva, Math 500, GSM 8K, Olympiad Bench, AMY 2024, and AMY-2025. For these tasks, which can have complex answers, we use GPT-4o as a programmatic judge to check the correctness of the final answer against the true answer. For the AMC and AMY benchmarks, we report the mean at 32 metric, while for the other math benchmarks, we provide accuracy based on greedy decoding. To assess general reasoning abilities, we evaluate on several tough benchmarks. MMLU Pro, which is a tougher version of the MMLU benchmark with more challenging multitask questions. Super GPQA, a large-scale benchmark for graduate-level reasoning with questions from 285 disciplines that are hard to find online. And BBEH, which builds on Big Bench Hard with new, more difficult tasks to better measure complex reasoning skills. For this category, we follow the experimental setup and report exact match accuracy using greedy decoding. Our framework is built on the easy R1 codebase. In each iteration of the R0 co-evolutionary loop, we use specific hyperparameters. The challenger generates a pool of 8,000 questions, which we filter for consistency to create the training dataset for the solver. A question is included if the number of answers matching the majority is between 3 and 7. When training the challenger, we calculate the uncertainty reward by sampling responses from the solver, and we set a clustering distance threshold for intra-batch repetition penalties. More details can be found in the appendix. In our results for mathematical reasoning, we present comprehensive findings that show our R0 framework significantly enhances the performance of language models on math tasks across various architectures. Our iterative training process consistently improves the base models. For example, with the Quen 3-8B base model, 3 iterations of R0 increase the average performance from 49.18 to 54.69, a gain of 5.51 points. Similarly, the OctoThinker 3B model improves from 26.64 to 29.32, showing the effectiveness of our self-supervised training loop. The results indicate a clear trend of improvement across iterations, highlighting the benefits of our co-evolutionary approach. In terms of general reasoning, previous studies have shown that training on reasoning-intensive tasks like math can enhance general capabilities. We investigate whether this effect persists when the training is entirely self-generated through R0. Our results demonstrate that this skill transfer occurs across all tested models, with Quen 3 to 8b base improving by 3.81 points and OCTOTHINKER 3b by 3.65 points after 3 iterations. This suggests that our method not only imparts domain-specific knowledge but also enhances the model's overall capabilities, allowing for successful generalization across different domains. Section Summary. In this section, we evaluate our R0 framework on various challenging benchmarks for mathematical and general reasoning, demonstrating significant performance improvements across different models through an iterative training process. Our results indicate that the self-supervised training not only enhances mathematical skills but also generalizes effectively to broader reasoning capabilities. Section Analysis. In this section, we conduct a series of detailed analyses to enhance our understanding of the R0 framework's behavior and effectiveness. For consistency, all experiments discussed here were performed using the Quen 3 to 4b base model, unless stated otherwise. In our ablation study, we aim to identify the contribution of each key component in the R0 framework. We systematically disable 3 critical modules one at a time and observe the effects on performance. The results indicate that removing any core component significantly reduces performance. The most substantial decline occurs when we turn off the challenger's reinforcement learning, leading to a drop of 3.7 and 4.1 points in math and general average scores, respectively. This underscores the importance of our co-evolutionary curriculum generation process. Similarly, disabling the repetition penalty negatively impacts performance, highlighting the need for diverse question generation for effective solver training. Lastly, turning off the task filtering module results in a significant performance drop, especially in the general domain average, which decreases by over 6 points. This filtering not only adjusts the curriculum's difficulty but also serves as a quality control mechanism by removing low consistency questions. Without it, the solver is trained on a noisy dataset, which hampers its learning ability. Next, we analyze the evolution of question difficulty and data accuracy to understand the co-evolutionary dynamic. We sampled 200 questions from the challenger's policy after each of the first 3 training iterations, creating 3 test sets. We assumed the external Oracle model, GPT-4o, provided perfect answers for all generated questions. We evaluated our internal models against these answers. The results show that the questions generated by the challenger become increasingly difficult. For example, the performance of the static solver drops from 59.0% on iteration 1 questions to 47.0% on iteration 3 questions, confirming that the challenger is effectively raising the difficulty level. However, the accuracy of the self-generated dataset declines from 79.0% to 63.0% by the 3rd iteration, indicating that as the problems become harder, the solver's majority vote becomes less reliable. This decline in data quality poses a challenge for the framework's overall performance. Despite this, the internal reward mechanism operates as intended, with the solver achieving scores of 51.5% and 50.5% on their respective question sets, demonstrating that the challenger successfully aligns question difficulty with the solver's evolving capabilities. Finally, we explore the synergy between our framework and traditional supervised fine-tuning when labeled datasets are available. We maintain the same GRPO settings as in our main experiments. We first establish a supervised baseline by fine-tuning the base model directly on the labeled data. Then, we apply our R0 framework, fine-tuning the resulting checkpoint on the same labeled dataset after each co-evolutionary iteration. The results reveal that our method provides significant additional gains, showing an improvement of 2.35 points over the direct training baseline. This confirms that R0 enhances performance rather than being redundant with labeled data, allowing the model to leverage supervised information more effectively and achieve levels of performance that standard fine-tuning alone cannot reach. Section Summary. In this section, we conduct detailed analyses of our R0 framework using the Qwen 3-4B base model, revealing that disabling key components significantly degrades performance, particularly highlighting the importance of the challenger's reinforcement learning and the task filtering module. Additionally, we observe that while the difficulty of generated questions increases over iterations, the accuracy of self-generated pseudo-labels declines, indicating a trade-off that impacts the framework's performance, yet our method still enhances results when combined with labeled datasets. Section: Label-Free Reinforcement Learning. In this section, we discuss label-free reinforcement learning, a growing area of research focused on enhancing large language model (LLM) reasoning without needing human-annotated data. Many methods in this field utilize the model's own outputs as a reward signal. This can involve using the model's confidence in its sequences, checking the consistency of answers from different reasoning approaches, reducing output uncertainty, or even applying random or negative rewards. These signals are often part of self-training loops, where models refine their most likely solutions. However, our approach, R0, eliminates the requirement for any initial dataset. We also explore self-play in large language models, where models assume dual roles to create a cycle of self-improvement without human input. This method has shown great success in areas like code generation, where one agent, the coder, writes programs that are then tested by another agent, the tester. More advanced systems take this further by generating their own problems, forming a flexible learning path from a few examples or even starting from nothing. Our work expands this concept to general reasoning tasks that do not have clear verification environments, relying instead on a reward signal based on the model's internal consistency. Lastly, we highlight reinforcement learning with verifiable rewards, RLVR, a widely used approach for improving LLMs across various tasks. Its effectiveness is evident in applications like relation extraction, interactive GUI navigation, search engine use, and multimodal alignment. While earlier versions depended on rule-based verification, recent advancements have started to incorporate more complex, model-based verification methods.